We all good?
Okay.
Yeah, welcome everyone. Welcome to the online audience as well. And as Mike says, start of a new year, a new session, or new session for 2023. We're revisiting that theme we started before Christmas of inviting speakers who have had the honor, shall we say, of being invited to compile chapters for the new edition of the Geology of Scotland. And so it's my very great pleasure to welcome a colleague from many years now, Tony Prave, Professor Tony Prave from St Andrews. Tony, I see as a sedimentologist, a process sedimentologist, a stratigrapher.
Don't tell anybody, no.
And so that kind of a geological animal. And so I find it particularly refreshing that the Dalradian chapter in the Geology of Scotland has been addressed by somebody who is in a position to speak with confidence or with experience about the sedimentology of that important unit in Scottish geology. For many, many years, it was tackled by people who saw it perhaps as more of a structural problem or a structural entity rather than a depositional entity. And so I look forward very much to hearing what Tony has got to say about the Dalradian supergroup, revisited, revised, yes, it certainly needs that, and refined. Well, we'll be the judge of that, and we'll ask Tony questions at the end. So I look forward to it, Tony. Thank you very much.
We good to go? Okay. Okay, well, thank you for inviting me. Thank you for coming to listen to me. I'll try and keep it to 50 minutes. The Dalradian is a fairly big package of rocks with a lot to tell. And so I will be here to try and tell that tale as best I can. I've chosen the 3 R's. Is it okay? Yeah, okay. I've chosen the 3 R's for a reason that I hope will become obvious as I go through the talk. There's gonna, it's not advancing for me. So problem number 1. Let's try this. No. So thank you very much, everybody. You can go home now. Try this one. No. Oh, there we go. Okay. All right, so let me back up. All right. Oops, jump. Bit slow. 4 parts to this talk today. A little trip down memory lane, and then the 3 R's. Revisiting, and what I want to do is actually focus on the start of Dalradian sedimentation and use that as kind of a theme that we're going to carry through the narrative of the talk. We want to place the Dalradian into what we can think of as Neoproterozoic Earth history. That is, take a step off of the island that we live on and compare it to what we understand and know from areas around the world that have similar aged rocks, and then refine the geological evolution of the Dalradian with respect to what has been learned over the last 20 years since the last volume or last edition of the geological evolution of Scotland. Just to remind everybody, and I guess I really don't need to do this because you all know what I'm talking about, this package of rock that's sandwiched between the Great Glen and the Highland Boundary Fault, the Dalradian, on the left-hand side, are the suite of characteristics that typify the Dalradian succession here in Scotland. It's a fairly thick package. How thick we could, argue, but we're certainly talking kilometers, many kilometers. Metasedimentary, meta-igneous rock package. From the north of Ireland right up through to Shetland, it can be traced. The age is Latonian. If you're not familiar with that particular term, this is early Neoproterozoic, 1,000 million, 900, 800 million years ago, up to about early Cambrian. For many people interested in the tectonic or geodynamical evolution of this part of at least the North Atlantic realm, and I will come back to that, it does archive our understanding of the makeup and breakup of what people now refer to as the Rodinia supercontinent. So it gives us some insight into supercontinental tectonics. And for me, what gets me out of bed in the morning to take a look at these kind of rocks up in the north of Scotland is that it is this record of cryogenian Ediacaran Earth history, this very critical period in Earth where it's perhaps arguably the second most profound interval of time in Earth history. It's certainly when the advent of animals happened and we had these severe climatic episodes that have now come under the moniker Snowball Earth. Okay, so that's the background. So we're going to take a wee trip down memory lane, and it is a very wee one. This is, I took some images out of the chapter in the Geology of Scotland, 4th edition, 2002, so 23 years ago, the Northern Highland and Grampian terrains. And if you'd read through that, the stratigraphic column is on the left of the Dalradian. I will not really get involved in any of the stratigraphic terminology other than to highlight at group level some of the units that I will be talking about and focus certainly on one formation, the Port Askaig-Tillite. But the take-home message from that chapter in 2002 of the 4th edition was that for the most part, the Dalradian formed in rift basins, that the starting of rifting was somewhere around 750 million-ish, plus or minus 50 million-ish years, and that the Port Askaig-Tillite was what was called the Varanger at around 600 million years old. And that's going to be what we're going to address in this revision, refining, and revisiting the Dalradian. Now, it's interesting because the trip down memory lane actually took me back to look at some talks and papers and things that that I did when I first came across to the island. You can tell from my accent, I'm not a native. I have been here 27 years this year. And what struck me coming is then a long-haired ex-colonialist was that every unit in Scotland was interpreted as being formed in rift basins. And so we're just going to do this little trip around Scotland. We went up to some of the oldest sedimentary rocks in Britain, if not in Europe, that haven't been really metamorphosed, the Store Group, a rift basin. Take a step to the next level, the Sleet Rocks, a rift basin. The Torridonian, a rift basin. The Moyne, a rift basin. I think you get the theme. The Dalradian, the early phase is a rift basin, the middle phase is a rift basin, younger. Now, what struck me was that if we took that at face value, it's 600 million years of rifting. And perhaps I wasn't quite polite enough back then when I said this is daft, because it is daft in one sense. And we know that you can't go anywhere in the world to see a piece of rock, piece of the earth that sits for 600 million years and experience nothing but rifting. Now, I love this. This is poetry. I have this on my door because this was a comment for a rejection of a paper that I had written to try and point out that I didn't think 600 million years of rifting was possible. Yeah, it's wonderful, you know? And the reason for it was because at the time the mantra was that the secret of the highlands, if it is Proterozoic, it is extensional. And that was the driving mechanism for trying to understand this suite of rocks. Now, we know that that's not true. There's people sitting in this room that have looked at these rocks and have recognized that the concept of rifting, it was for its time. But we now know, since the publication of the 4th edition and what you will be reading in the 5th edition, is the 5th edition? 6th, 5th, yeah, is some of the work that Martin and others have done that has shown that some of these previous interpretations of rifting were suspect, if not wrong. And so what I want to do is raise that same question for the Dalradian. Okay, so this is the revisiting part, and that is the most enduring concept we have for the Dalradian was formed in a series of rift basins. Okay, yes, lots of evidence for rift basins, or extension, let's say. You know, beautiful intraformational conglomerates and breccias that are being shed off of what are interpreted as sedimentary normal faults, things like the Scarba conglomerate, the Barravulum boulder beds. And we see the pillar lavas and the Tavelic, these volcanic units, which clearly, you know, mantle source extension of continental lithosphere. This is occurring, there's no doubt. If we look at the stratigraphic column of the Dalradian, the thing that's interesting from a supergroup perspective is that all of that evidence is really in the upper half, okay? And the one elephant in the room that we really can't get around is the fact that for this entire succession of rocks, the most studied, most mapped suite of rocks probably in the world is there's one depositional age. Let's just call it 600 million for simple numbers. We're all geologists, we can't do math, so we'll just keep it at 600, okay? That's it, and it's sitting up near the top. So what it does is it begs the question then, what about this lower bit? You know, the lower half. That is what we think of as the Grampian, Appin, Glen Shira group rocks. Let's take a look at them in terms of what Graham said, that, you know, I approach rocks thinking sedimentologically, which is what I do. Now, what we have to do to answer that question, what those rocks look like, is go to other places. So I'm going to take you on a bit of a tour to places that I've worked in, lucky enough to work in, and to answer what we want to think about in terms of extensional basins for the Dalradian. And remember, it's continental crust that's being extended. We're not talking about oceanic crust here. This is one of the most extended bits of continental crust on Earth. This is the western part of the US. You can see geographically where we are: Denver, Sin City, Las Vegas, Los Angeles. Rocky Mountains, the stable bit of the Colorado Plateau, the Mesozoic arc of the Sierra Nevada, the plate boundary that we have with the San Andreas Fault and the Garlock offshoot. And what we're going to do is take a look at what continental extended lithosphere looks like in probably, like I said, the most iconic part of the world for extended continental crust, the Basin and Range province. And we're going to go to a place, Death Valley. I don't know if any of you have been there. If you haven't, it should be on your to-do list to go see, because it is quite stunning. And just to give us a sense of scale, because if we're going to infer that we can reconstruct environments of deposition in sedimentary basins, we want to do it to an understanding by the mechanisms of processes that's actually driving extending continental lithosphere. And that's our homeland to scale for the Basin and Range. And that's what an extensional basin looks like in continental crust. This is Death Valley. Bad water is that little dot there. It's 90 meters below sea level. In terms of the structural geology, the Black Mountains is the uplifted footwall. That dashed line that I have is the frontal fault of the Death Valley Basin, the Black Mountain front. And this is the rotated range block of the Panamints. And to give you a sense of scale, in the distance, Dante's view, that's a mile high. So that's what we're talking about in terms of thinking about rift basins in continental crust. To give you another sense of scale, where I'm standing, looking down to where you see the juncture or where that canyon feeds in between the range, that's a little over 1,000 meters of elevation difference. And so basically we could stuff Ben Nevis almost in from where I'm standing down to where that canyon cuts through the Panamint range. I like this particular image because, again, going through memory lane, I took this image almost 42 years ago to the day, because that light-colored band of rock that you see running across the Panamint range was my master's study, my master's degree in terms of doing sedimentology of Cambrian units. That's the arable sandstone, pipe rock, if you will, okay? And this unit I traced from essentially northern Mexico up to the White Inyo Mountains. So basically somewhere across the size of Scotland. But we're not here to talk about what I did then. We want to talk about what we can do now. This is a bird's eye view looking down at that same view, more or less. And what I want to impress upon you is this, is that if we're going to invoke a geodynamic or tectonic process that is operating on Earth's surface, then there is a supracrustal response that we call sedimentation that has particular characteristics that are keyed to that particular tectonic process. This is how we reconstruct sedimentary basins in the past. We look at the facies characteristics, the sedimentary characteristics that allow us to tie and say, yes, this was an extensional basin, or this was a foreland basin, or this was a pull-apart basin. It is the sediments that infill that hole in the ground that is the fingerprint of those tectonic processes. In this case, what we see in terms of the sediment feed into these basins is, as it says there, the sources are fairly local. Everything is constrained. You're coming off the rising footwall and the hanging wall, excuse me. Multiple feeds, it's all orthogonal, axial flows. And if we think about what's happening to those sedimentary packages, as they feed laterally, they undergo fairly rapid facies changes. So you go from very coarse alluvial fan braided fluvial into very fine grained lacustrine muds, or if you want to do submarine, instead of subaerial, subaqueous complexes, submarine fans into, marine basinal settings. And I'll show you some of those as we go along. That is the facies characteristic, and that's the way I approach looking at deformed orogenic belts if we're talking about supracrustal successions. Now, when I say rapid lateral and vertical facies changes, what do I actually mean? So we're going to go on a little hand-holding picture tour across a classic extensional basin that has been exhumed due to base level fall of the Amargosa River, carving out what is this late Miocene China ranch beds. This is just south of Death Valley itself. And we're going to go on a lateral transect of time equivalent units, 1, 2, and 3, over a distance of about 2 kilometers. And if you were to do that transect, this is what you go across. You go from what the West Coast geologists call fanglomerate, that is sediment that's formed in an alluvial fan. Very coarse grained, very poorly sorted, very angular. This is what we teach first-year students, right? Feeds into these coarse braided fluvial deposits, and that very rapidly goes into these finer grained, and in this case, lacustrine muds, marls, and limestones. That's a little mine. The hole above was made during the Depression when people actually lived there because they lost their homes in Los Angeles. So laterally rapid facies changes. You see the same thing happening vertically. This is Zabriskie Point. It's also a Miocene age packet of the same types of rocks that we're talking about. Vertically, as you go upward over distances of tens of meters, you go from lacustrine up into braided fluvial, and these things stack one on top of one another, etc. And laterally, you see that same facies change. Braided fluvial coarse deposits feeding in laterally into finer grained deposits. Now, I know the purists in the room would say, yes, but the Dalradian is marine. Okay, I said earlier that you see the same kind of characteristics in subaqueous extension continental crust, which you do. We can go to our back garden, the North Sea. This is just a crude cross-sectional view of what the Tories have made money on in Britain. The Bray member, this is the very first, or one of the very first fields that were found. And schematically, you can see this transition from coarse submarine fan complexes into finer grained basinal muds and shales. This is true on the other side of the Atlantic as well. You can go to Brazil, see the same type of pattern occurring. These laterally and vertically varied facies. And it doesn't matter if the extensional basin is sitting there at the continental crust oceanic transition. You can see the same aspects, whether you're looking at Triassic, Jurassic basins on the east coast of the US, whether you're looking at pop-up basins that are a result of slab rollback, things like the Apennines, or in pull-apart basins like the Ridge Basin or the Hornland Basin. All the same facies characteristics. If we want to see what they look like physically, well, there they are. My PhD area on the left, the opening of the Bay of Biscay, feeding in these coarse-grained turbidites, debris flow deposits, all locally sourced. The Neoproterozoic at Death Valley, it was an extensional terrain in the past. We can see these coarse-grained deposits, debris flows, etc. And we don't have to go to somewhere exotic. We can get on a boat, go out to Scarba, and see the Scarba conglomerate and seeing the same types of facies that are being shed into basins that are undergoing active extensional tectonism. So that's what we should see. So, in a nutshell, local provenance, poor sorting, mixture of very angular rounded clast, rapid lateral varied, and rapid lateral and vertical facies associations. That's the motif. Any extensional basin, anywhere in the world, at any time in Earth history. So this is our mantra. If it's Proterozoic, it's extensional. This is the part of the Dalradian the Grampian group, just sitting south of Inverness, that has had the fingerprint of saying that we're looking at extensional tectonism. Yeah, thank you. Good man. Yeah. That has been the underpinning for the idea that the Dalradian started out life as a rift basin. So we're going to take a look at this particular set of rocks. That is the image of Death Valley to scale. All right, so the scale of the Grampian group basins and what we see, what I've just showed you in terms of extended continental crust. This is something that we should be looking at in terms of the rocks that we see in the Coriacic or Strathtumel basins. This is a very simplified map of the key area. The red rectangle is what we're looking at here on the right. I've just rotated it slightly to get it from north going off to the top right corner. And we're just going to take a look at this in terms of the key features. We have the basement, that is the continental crust that's supposed to be the uplifted footwall or the fault blocks, the Glen Banker group. This is these migmatitic rocks, sorry, the Badenoch group. This is these migmatitic rocks that form the so-called Rift Basin High, just like the Black Mountains or just like the Panamint Mountains, as I showed you in Death Valley. You then have encasing that, the Grampian, oh, I'm sorry, this might be what happens when you have a Mac program or a Mac PowerPoint sitting on a PC. The brown purple colors is the Grampian group. We have the Caledonian granites, these white blobs, and there is, and I'll come to the Glen Shira group, sitting there isolated, that green patch in the corner. And the key to the highway for us, because I've highlighted these in blue, is this little strip of rock that's been interpreted as the Appin group. So we have the Grampian group and the Appin group. So the Appin group is sitting well above the base of the Grampian group, and the idea is that it is onlapping this paleo high of these basement rocks, the Badenoch group. There are the basins. Remember the motif. This is what we should be seeing, given that we are in proximal positions to the basement highs, the inferred basement highs. But instead, what you have across those basins, not exactly the same everywhere, but by and large, this type of depositional sedimentological facies, these relatively fine-grained, wonderfully developed turbiditic rocks. Centimeter, decimeter thick beds. People say, yes, but the Glen Shira group, it's very coarse-grained. Therefore, you do have these coarse-grained facies. The problem is that yes, they're coarse-grained, but you know, all coarse-grained rocks aren't always the same. Clasts are rounded. Compositions are not local. Facies are similar over hundreds and hundreds, if not thousands of meters. They don't change very much. And importantly, when you look at how they have been sourced, particularly from detrital zircon studies, they're not related to any of the so-called basement rocks around them. They're being derived from, as best as people can tell, a suite of rocks known as the Rins complex, which is about 200 kilometers. The nearest present-day exposures are 200 kilometers away on Isla. So we have a package of rocks that does not have any of the facies characteristics that are archetypal for having formed and being deposited in rift basins. So the question you have to ask is then why were they interpreted as a rift basin? And the reason is that you have sitting there on the left-hand side, rocks that were interpreted as Appin group sitting on basement rocks. That is, the entire Grampian group was missing, and therefore this must have been some high, and therefore if it's a high and it's a basin high and you're forming basins around it, these must have been extensional basins. The evidence comes down to geochemistry. You know, there was a very dear colleague, now departed, once made the comment that, you know, desperate rocks call for desperate measures. And it's tough. These rocks are tough to work with. You know, how do you correlate rocks that have been polyphase, deformed, etc.? And so this was an effort to try and understand what these units were with respect to correlating them across the Dalradian outcrop belt. And the existence, as I say, of the Glenbanker High, excuse me, is based entirely on that interpretation that the limestones, these thin limestones that occur to the margins of the Glenbanker High, were Appin group. And that correlation is entirely based on looking at iron, magnesium, calcium ratios. People have looked at the geochemistry of those rocks. Sometimes it works, sometimes it doesn't, in terms of matching up units that you think are correlative because of major element and trace element and rare earth element chemistry. And I'll show you some new data in a minute. So that is the evidence for the Dalradian having started life out as rift basins. And that's the evidence. This is the paper. And the idea here is the axes that you see are ratio plots, iron to calcium oxides, magnesium to calcium oxides. This colored interval is the iron, magnesium, calcium ratio space that is defined by Appin group limestones. And you can see the various units that have been used to do this. And I'm highlighting two in a red box because those are our key to thinking about the Grampian group rocks in these two basins separated by these inferred basement highs, the Kinlochlogan limestone and the Kincraig limestone. Okay. Now, I want to stress as much as I can that we need to have the geographic representation of where these units are relative to one another to one key fault system. So there are the two localities that have been key to identifying Grampian group limestones, the Kincraig rocks, and Appin group limestones, the Kinlochlogan rocks. In betwixt is Cool Farm, a central cornerstone to this idea of the onlap of the Glenbanker High with the Appin group. Two other exposures of carbonate limestones that I'm not going to talk about in detail, but I will bring some data in from those two, are Ordban and Dolnain Bridge. These are these limestone units that are occurring in this lower part of the Dalradian supergroup, the Grampian, or in the Grampian group. And what I want to highlight particularly is this major fault system. I have trouble pronouncing words in English, so I'm not going to pretend I'm going to pronounce Gallic words correctly. Graham, you might be able to, but I assume this is Anik Bayag Inverpatic Marquis fault zone. I'm just going to call it the ABIM fault zone. All right. And here it is, just to blow it up and have this in your mind. We have rocks that are interpreted as the Appin group limestones, the Kinlochlogan and Cool Farm, and what everybody agrees is Kincraig, these Grampian group rocks, separated by the ABIM fault zone. Okay. So now let's take a look at some geochemical data, because when you go there and walk around, many of the encompassing units around these limestones at Cool Farm and Kincraig don't look very much different. These are politic Semitic rocks that are sitting often at, upper green schist, lower amphibolite facies. So it's the limestones that are the key to the highway, or the marbles. Yeah, oof, here we go, okay? I'm going to make this straightforward, I hope, by highlighting what I want to stress from this data set. These are data that were just generated about 3 months ago. I sampled the carbonates this past summer. And what I want to highlight is that if we look at various elemental discriminators, which people use, and these are common, this is not me cherry picking. These are common things like thorium, scandium, titanium, aluminium, ternary plots of these. There is this fairly close clustering between Cool Farm and Kincraig. If we come down to look at things like rare earth element in these spider plots, these spider diagrams, right? what we can see is there is some differentiation between at least one of the limestone units, but for the most part, the Cool Farm, Kincraig limestones plot one on top of one another. And this was highlighted by Thomas and Aitchison themselves saying, well, you can't really rely on just pure elemental data to separate these out. And therefore, we need to use ratios of calcium, iron, and magnesium. So, okay, I did that, or I and my colleagues did that. There's the plots, the log plots of the iron, calcium, and magnesium oxides, Cool Farm, Kincraig, plot together. And if we then compare them to the Kinloch-Login data, they plot together. So either the geochemistry is not useful in discriminating these particular limestone units, or perhaps they have been miscorrelated. There is another suite of geochemical data that has been used successfully, and this is carbon isotopes, stable isotopes, the ratio between 13 and 12 carbon. It's been used worldwide to create correlations locally, regionally. Some people have done it globally. I don't want to go there at this point. I just want to highlight that it is a discriminator. Carbon is 1/5 calcium carbonate. It takes a hell of a lot of fluid to modify that ratio moving through it. And so if we do carbon isotopes on those particular limestones, and the plots that you see here, the x-axis is delta C13, the y-axis is oxygen 18. There is this differentiation fairly nicely, statistically significant as well, in terms of identifying Cool Farm, Kincraig, and Kinloch-Login sitting off by itself. If we then put those into the context of the Grampian and Appin group, we have a fairly nice distribution showing this differentiation between these limestone units, one of which plots within Appin group data very clearly. The one that was interpreted as Appin group, the Kinloch-Login, the other two plotting in the Grampian group field. Now, in the world that I inhabit, in terms of trying to understand Neoproterozoic Earth history, carbon isotopes is one of the tools in our toolkit that we use. And typically what you can find is that many of these data sets, there is a reasonably systematic trend in the values. And so if we plot the carbon isotope values in a reasonable stratigraphic framework, we get, and when I say a reasonable stratigraphic framework, one that makes sense in carbon isotope space, we get a fairly systematic pattern from the base of the Grampian group up through these limestones up towards the Appin group. Okay? So what I think we can conclude from that is that the log ratio oxides of iron, magnesium, and calcium really are inconclusive as a differentiator, as a means for differentiating the carbonates. What we can say, whether or not you believe, want to use, I don't want to use the word believe, whether or not you trust the carbon isotopes to be a pure correlation tool, but what we can say is that there are 4 characteristics that the marbles that Cool Farm and Kincraig share relative to differentiating them from Kinloch-Login. That is, each group has an internally consistent carbon isotope signal, that the carbon isotope values of those 2 units differ from the Appin group, that the carbonate rocks that are associated with the Semitic politic units are comparable at each locality. There are not vast differences between them. And importantly, quite often the absence of evidence is key, as much of a key as what evidence is present, is that when you look at Cool Farm and Kincraig, that characteristic trinity of quartzite carbonate and graphitic schists that mark a lot of the Appin group everywhere else in the Dalradian outcrop belt is not really present. So the conclusion is that the marbles at Cool Farm and Kincraig are best interpreted as Grampian group. Combine that then with the fact that the Grampian group rocks that are sitting around these inferred basement highs do not have any of the sedimentological features associated with rift-related sediments, then what one can say is that this is probably not the right way of thinking about the deposition of the Grampian group at the start of Dalradian supergroup sedimentation. There's no geological evidence. It was all based on the assumption that these Iapetus group rocks were onlapping the basement. Now, right, is this just British navel gazing? And, you know, I think, yes, we want to understand the rocks, the geology of this country that we live in as best we can. But the thing is that it has impact outside of Scotland. And I think you all know that. And I'm just showing you one example of why it's important to get this right. Because we have people coming in and telling us about how supercontinents form, how plate tectonics works in the past, based on rocks from Scotland. So if we are interpreting these rocks as extensional and rifting, then that must mean that this supercontinent of Rodinia was breaking apart at that time, okay? But if that interpretation of the rocks is wrong, then the interpretation of what we think of the evolution of a Rodinia supercontinent is wrong, at least from a Scottish perspective. So is there something that we can say that is positive in terms of thinking about how these rocks may have formed? And so since the 4th edition, the last 20 years, a lot of work has been done to understand the paleogeography of the North Atlantic. And the accepted model at the moment is this. We have this rotation of Baltica in its collision with Laurentia happening first in a relative perspective of today in the north, with Baltica rotating in a clockwise manner to open up into the Asgard Sea and create these two orogenic episodes separated in time by about 100 million years, the Rhinelandian in the north, the Neudartian in northern Scotland and northward. And what I've highlighted in blue is an inference then that the Grampian Iapetus group rocks represent the flysch molasse sediment being shed off of these collisional orogenic belts. In other words, here is the archetype of a four-limb basin related to continent-continent collision with India, the subcontinent, colliding with Asia to give us the Sewalic four-limb basin highlighted in pink. There is the North Atlantic paleogeography during early Neoproterozoic time. Interestingly enough, the Himalayan orogenic belt is a pretty close match spatially for what is inferred to be this Rhinelandian Neudartian orogenic belt with the strike length of Baltica intersecting with Laurentia. And like any orogenic belt, it gets eroded and it sheds sediment. And the inference is this is what we see with respect to the Grampian Iapetus group rocks. So what is the flysch de molasse? Very simply put, two terms that are used from the Swiss flysch molasse basin, the erosional material off the Alpine orogenic belt just to the north of the Alps in the Rhone basin, and also in the Po River basin to the south. But here would be the molasse and flysch of the Himalaya in terms of the Sewalic basin that is subaerial or non-marine, feeding into the submarine fan complexes of the Bengal fan and Ganges fan complexes, the flysch, the turbidites. I couldn't find a nice cross-section for that, but here is a classic flysch de molasse succession in our neighbor across the pond. This is the Central Appalachian Basin, and this is mid-Paleozoic flysch de molasse. And basically what you would see in every flysch de molasse foreland basin in the world is this transition from deep marine turbidites up into shelf or fluvial types of facies, the molasse. Well, if we look at the Grampian group rocks, where people have studied the sedimentology 30, 40 years ago, classic work, fence diagram showing what happens in terms of what one sees stratigraphically and sedimentologically is this progradational shallowing upward trend. And if we put rocks to it, turbidites, deeper water flysch going upward into shelfal, shallow marine Appin group rocks over thicknesses of several kilometers. The facies fit, the stratigraphy fits, the lithologies fit, the source areas fit, and therefore I want to conclude that what we're looking at is a flysch to molasse transition and not an extensional rift basin. And I put this up saying that sometimes you do have to reinvent the wheel. And what I mean by that is this. Graham made a very cogent comment right at the beginning that the initial studies of the Dalradian were focused on trying to understand the structure. And these were beautifully detailed studies identifying different phases of deformation. And so these rocks have been mapped in exquisite detail. And therefore, if you're going to want to throw out part of an interpretation, you don't want to throw out the baby with the bathwater. If the rocks fit sedimentologically, that's one thing, but do they fit structurally? Okay. And the wheel, what happened? Who can see this transcript? I've already bored somebody, they've clicked. And what I want to do is reinvent the wheel by highlighting work that was suggested way back when by a couple of people that looked at these rocks and looked at the structures and said there is evidence for original reverse or thrust faults. And if we go back to the framework, the structural framework, a very simplified one, of that particular region, highlighting those two key areas of what were interpreted as Appin group rocks. This is a cross-section inferred from a geophysical transect, and we all know how woolly some of these can be, but nevertheless, if you have that, and this is what we have, showing the particular cross-sectional view of that area, what I'm suggesting is we can reinterpret it by reinventing the wheel and using Piasecki's ideas and others to suggest that this ABIM fault had an original reverse or thrust displacement on it, bringing up what would be in the hanging wall, the rocks to the northeast, the Grampian group and basement up against the Appin group rock that sit in these very tight synclines, which in most people, when they think about structural relationships and thrust faults, look at footwall synclines. Okay, so in this manner, the sedimentology fits. If we open ourselves up to saying that, yes, some of these structures actually had a thrust or reverse displacement on them, we can interpret those rocks as part of this fold belt associated with compression to give us the structures that we see. So what I would suggest the take-home lesson would be is there's no lithological evidence for the existence of rift basins. The structural template of the Northern Highlands likely had some reverse faults, and a viable scenario is that Dalradian sedimentation was initiated as a foreland basin. It fits with what is known with the North Atlantic tectonic framework that's been established over the last 20 years. Now, for part 3, revisiting the Dalradian's place in Earth history. And we're going to do this by looking at 2 data sets. One is looking at Earth history through what we can think of as the lens of climate change. And what is known globally is that there were 3 major glaciations that affected our planet during this Neoproterozoic time slice. They're given the names Gaskiers, Marinone, and Sturtian. There's the ages that are associated with them. Those 2 are the snowball Earth glaciers. This concept is shown here artistically, where the ice age was so severe that you essentially had ice extending from poles to the equator. We could argue about the exact nature of those, but this is pretty much the accepted idea at the moment. Again, something worthy to test. We can also look at Earth history through the lens of carbon isotopes. I talked about these previously. This is a very simple diagram showing carbon isotope trends through Earth history. The x-axis is time, going from more or less the formation of the planet around, well, not the formation, but the Neo-Archean 3.5 billion years ago to the present. And what you see in terms of carbon isotope space is that there are really two periods in Earth history where the carbon isotope signals seem to have gone a bit haywire. We see these big excursions. The big one you see here at around 2.5 billion years ago, the Lomogundi-Yatuli event was associated with the Great Oxidation event. And the excursions that you can see associated with snowball Earth, the advent of animals, the biosphere, the locking up of carbon into calcium carbonate shells and tests, this influenced the carbon cycle. That is when the Dalradian was deposited. So can we marry these two data sets that are known globally and bring them into the Dalradian? This is now a blow up of the kinds of patterns that one sees with the carbon isotopes, the pink squiggly line. The people who've constructed this called this the bumpy ride. And all I want to do is highlight two things. One, the fact that you have those three glacials. When we see Neoproterozoic sections worldwide, we can document them most of the time, not always. And these excursions, they've been given names, they've been recognized globally. And I'm going to highlight one because I'll come back to it towards the end, what is known as the Shuram. This is the deepest negative carbonate-carbon isotope excursion in Earth history. In 4 billion years, there is nothing as deep and extensive as this. It goes down to -10, -12 per mil carbon isotopes. Okay. And that's the question. How does the Dalradian fit within this framework? So to answer that, of course, we got to go to some exotic places because we have what everybody recognizes and accepts as one of the hallmark exemplar cryogenian glaciations anywhere on the planet. This is the work by Tony Spencer and others. He's probably talked to this group. I think Graham said you're going to have somebody coming up. You'll have Bruce Lavelle coming up to talk about this. That is Tony Spencer on the left, pointing to what's called the Great Breccia. Here on the right is something called the bubble. You can see the person circled for scale. It's a huge ice rafted block. It's a push, a glaciatectonic structure. It's ice push structure. You can see these along the coast of Norfolk, Denmark, and other places. It's when ice moved over a substrate, folded it underneath. So classic ancient glacial features that are preserved in the Portascae. But what one is it of these three? Sturtian, Marinoan, or Gaskiers? And so what I'm going to do is do the same thing. I'm going to take you on a bit of a journey to show you what evidence we have elsewhere so that we're not just looking at the Dalradian and saying, oh, this is what I think it is in the Dalradian. Let's compare it and contrast it to what we can study from places around the world. And I'm going to take you to the Otavi Fold Belt in Namibia and somewhat less exotic, perhaps, Loch Swilly in Donegal. Okay. This is a very crude, simplistic cross-section of the Neoproterozoic succession in Namibia. And I'm going to highlight just two things on this. I hope you can see that. I've highlighted the glacial units that represent the snowball earth rocks in Namibia. They're given the term Gaup and Chuas, Marinoan and Sturtian. I also want to highlight one of the key carbon excursions that are associated, carbon isotopes excursions associated with what's called the Myberg cap carbonate. Now we'll step into the rocks that we know. I've put this, the geology of Donegal, a study of granite, because Wally Pitcher was brilliant. The best stratigraphic cross-section of the Dalradian is found in a book about granites. You know, go figure, right? Wally recognized, you know, these, there we go. You know, I've highlighted the Portascae tillite. I've highlighted a couple of units in Ireland, this Cranford and Strelinsky conglomerate. And I've highlighted some things that I'll show you some photos of that I'm going to convince you we have the Marinoan glacial in mainland Scotland. What I want to point out, so that we're all aware of this, is that quite often, worldwide, the Sturtian, older glacial, is very extensive, very well developed. It's not at all unusual that the Marinoan glacial has areas that are quite patchy, just little lenses that are preserved. It's not some huge diamictite. And let me show you that. There is the Namibian section. I've colored in blue where you walk along that contact and you'll find just little skiffs and lenses of the diamictite. Above it, that entire mountain face is the cap carbonate, the meltback phase and precipitation of carbonate following the glacial phase. Slightly less well exposed, Loch Swilly. This is what you see. On the left, the Donegal rocks. On the right, the Namibian rocks. There is these beautiful glacial units that we can see. We can do this comparative geology with the cap carbonate. On the left, and I'm going to show you a series of these. On the left is the Loch Swilly cap carbonate. Sorry, the Donegal cap carbonate. On the right is the Maranoan. The very first deposit of a cap carbonate is this isopachus cemented and sheet cracked dolostone. It gives way upward into these lamanites and rhythmites, and it gives way upward then into these thin-bedded allodapic limestones. This is the world over. This is Donegal. This is Namibia. What does carbon isotope space tell us? So this, now published whatever, 15, 16 years ago, is the Cranford limestone, what we see in Ireland. That's the trend for the Maranoan cap in Namibia. It's this beautiful match in this carbon isotope trend that I highlighted on that stratigraphic panel, which shows this downturn from values that are around 0, -2, down to -6 or 8, okay? This is what you see the world over. And to prove that point, here is, we've gone back to Death Valley. The top of that mountain is the platform shallow marine Maranoan cap carbonate. That's what it looks like in its basinal facies. Hundreds of meters reduced down to a few meters. The mountain in the background that forms the skyline on the left is the Kingston Range. That's a distance of about 60 kilometers. So this entire cap carbonate collapses down to a fairly thin unit. Same is true in Namibia. There's the platformal shallow marine. If you go into the deep part of the Namibian basin, that's the cap carbonate. It's caught up in a fold, so this is folded over on itself. You can see the pen for scale. It's at sillimanite grade. It captures the same carbon isotope signal. So the question then is, if we follow Wally Pitcher's cross-section going from shallower into this basinal facies into Scotland, what would the Maranoan equivalent cap carbonate look like in Scotland? Well, remember, that's what it looks like in Namibia under sillimanite facies. And this is what it looks like in Scotland under amphibolite facies. This is the little brown limestone of Lapworth through Perthshire. What about the glacial? We showed you these beautiful dimictites. If you go into the basinal settings, you don't get thick dimictites with the Maranoan. You find isolated drop stones. Icebergs are calving and melting, giving us these drop stones. There's one in Namibia, there's one in Death Valley. If we go to the equivalent interval in the Dalradian, you find drop stones, quartzites and carbonates. This is just below your level of the Ben Lawyer schist. All right. So we have then in Scotland a record of a Maranoan glacial cap carbonate couplet that in every way, shape, and form looks like the Maranoan glacial cap carbonate couplet in basinal facies worldwide. So if that's the case, what about the Gaskier's equivalent? And yes, everybody knows about the McDuff boulder bed. Everybody goes and takes a big picture there and it just north of McDuff, this big block of granitoid with a hammer. But when you walk around, you see some beautiful little drop stones. You don't need big, size doesn't matter here when it comes to drop stones for glacials. You can also see this on the south coast, Loch Nakill beds. And there's a little granitoid drop stone in these Marley mudstones. That's a pound coin for scale. All right. So we have Gaskier's equivalent. We have Ediacaran equivalent. Come back to the Sturtian because I'm going to do a little side tour now to convince you about how we can tie the Dalradian into Neoproterozoic Earth history not just using cap carbonate chemostratigraphy, but remember I talked about the Shuram. Well, to find that, we need to go to Shetland. So we don't want to leave Shetland out of the picture. Values -10 to -12. Nowhere else, sorry, at no other time in Earth history do carbon isotopes attain those values. This was published again 14 whatever years ago. This is the trend of the carbon isotopes for the limestone units that are in Shetland. Oldest at the bottom, youngest at the top. The x-axis is carbon isotope space. And I point you to the Gurlsta limestone. This is the Shuram excursion, preserved in the Dalradian succession in Scotland. We also on Shetland have the preservation of that cap carbonate trend in the lower whiteness limestone, where the values descend down to -6 or so values like we see in Maranoan cap carbonates everywhere. So Ian Fairchild and colleagues have now been putting this data together. They have really focused on the Port Askaig. And the one point that I haven't made is looking at strontium isotopes. And this is what I want to highlight here. This is a diagram out of Ian's most recent paper in which he's linked the Sturtian strontium isotope curves globally to what the data have been collected through the Dalradian, along with all the various other data sets that I've just shown to you, the Strelinchy, Cranford, Easdale, Maranoan, McDuff, Loch na Kill, etc. beds, being able to tie those into the Gaskiers in the Maranoan equivalent. And therefore, we have this beautiful stratigraphy now that matches. But for those of you who are Dalradian aficionados, there has been this bit of a fly in the ointment, because there is a rhenium osmium age on the Bellahoolish slates that sit at upper green schist, maybe lower amphibolite facies, that came out at 659, 660. So how do you reconcile this? Well, we don't have to, because the authors that have published that age a few years later, by looking at units around the world, published this in their PNAS paper. Additional tests in geochronological constraints are necessary to more fully resolve the complexities of the Dalradian. A very, very nice way of saying we doubt that age. All right. So if we put the Dalradian then in its place in Earth history, the physical stratigraphy says that we have the 3 glacials matched with cap carbonate character. We have the carbon isotope excursions and the strontium trend that is global. These are reproduced from Ireland through Scotland to Shetland, and they're compatible with what we know globally. If we accept those ages, the idea of how much time is locked up in the Dalradian, we can subdivide it into upper and lower, and we're looking at a fairly tasteful about 100 million years per upper lower Dalradian, which is what you expect for these types of stratigraphic successions globally. So if we then come back to putting this into the North Atlantic realm in terms of the tectonics, we can build a pretty nice story, I think. We can look at what I've highlighted in brown is that Molosse phase of sedimentation associated with the Neudartian orogeny, this rotational collision as Baltica collided with Laurentia. We can think of then the Blerathal-Bellahoolish subgroups as what we recognize in foreland basins worldwide, the successor or overstep basins. We can tie that to a time if we accept that the Port Askaig is Sturtian at around 720, 760 million years ago. We have all the extensional activity in the Argyll group and Southern Highland group. So yeah, great. That is when Rodinia started breaking apart, not at the base of the Dalradian, but up near the top. And then we step into the Iapetus passive margin. A beautiful story. Breaking news. 3 weeks ago, papers published by Norm Moles and David Selby. This is taken directly out of their paper, diagenetic pyrite, overgrowing the barytes up in Eberfeldy. They got an age on the pyrites, 604 million. Their conclusion, everything I told you is, to be polite, bullshit. It's wrong. Because, according to them, on diagenetic pyrites, the Port Ascade really is the Maranoan, 600-ish million years. They use the age that I've highlighted in blue, the 660 age, which the authors that worked on that age said, we got to question it, saying, no, 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 it's correct. Our 604 age, well above the Port Ascade, on diagenetic pyrite, is a syndepositional age, and therefore the Port Ascade really is 600 million years, and everybody else is wrong. So I thought I'd do a little tick box exercise. Geology is always about trying to balance the amount of observational data, empirical data, experimental data. So if we just look at how we understand linking stratigraphic frameworks locally, regionally, and globally, we have a stratigraphic framework of 3 global episodes. It fits the revised view of the Dalradian. If we do stratigraphic framework of cap carbonates, that fits. If we do strontium isotope, if you don't want to listen to calcium or carbon isotopes, the strontium isotope trend is absolutely solid. It fits. The carbon isotope excursions, I showed you the one, but you can match up many of them. It's compatible globally. Well, according to Moles and Selby, the Rios age is depositional. But I think it's as easily explained as being a diagenetic age. Now, that's just not me wanting to be cranky and fussy, but I'm going to highlight that one age I pointed out to you at the beginning, the 600 age. The volcanic units that we know are occurring at the top of the pile of Dalradian rocks, those ages overlap. I cannot understand for the life of me how you can look at diagenetic pyrites and assume that they're a syndepositional age and not think of a 600 age as being pretty close to thinking about the volcanics and the fluids that would be associated with those. But if there's one take-home lesson for me to conclude with, it's that the secret of the highlands, if it's Proterozoic, it's complicated. Hello. And these beautiful rocks that are deformed and mostly covered, I guess the only message we can take is keep calm and stay open-minded. Thank you.